All right, hello. We're going to go through our first set of weak acid calculations. We are going to start off with just finding the Ka of a weak acid, usually based on the initial concentration of the weak acid and its provided pH value. So for this first question, this all comes from section 18.4 in your textbook. We have our phenyl acetic acid, which we're going to simplify here just as HPAC, which is just for ease of writing everything out like our balanced equation. We're given here the concentration of the weak acid and then also provided the pH of the weak acid. And again, we're going to be finding the Ka. So we're going to be using the ice table method and going from there. So this is going to look very similar to our equilibrium unit. So let's start off with a balanced equation. We're going to have the weak acid HPAC. We're going to show the reaction that it's going to undergo with the water. The weak acid is going to be donating a proton to water. So water here is acting as a Bronsted-Lowry base, which is going to create, sorry about that, this is going to be tricky the first time. We're going to have our H3O plus ion, which is our hydronium. And then we're going to have the remaining negative ion, which is the conjugate base of our weak acid. So there we have our expression. Our Ka expression is our products over our reactants. So we're going to have our H3O plus, the PAC, over the initial weak acid concentration. All right, and as you can see, I purposely left out the H2O because it's a pure liquid, so it's not going to go into our expression. So then from there, I'm going to go ahead and create my ice table. I'm going to be taking out water from it. And then I know from my information, I was given the weak acid's initial concentration. I didn't start with any hydronium, which we'll talk about kind of the assumption we're making because we know that water auto-ionizes into hydronium ions, and we'll do a check for that shortly. And then 0 for the negative ion. So we know then that it's going to proceed to the right. So based on our balanced equation, this is going to be minus 1x, and then our two products are going to increase by x. So then I'm going to create the sum of those two columns as so. All right, so we have our balanced equation, we have our ice table set up, and we have our Ka expression. So in order to go from here, we're going to start and focus in on our hydronium ion concentration, which we're going to get from the pH value. So based on our earlier work last week, we are going to be able to find that hydronium ion concentration by doing 10 raised to the negative pH. So it's going to be 10 raised to negative 2.62. And remember from last week, hopefully you caught that this has just two significant figures. So when I record my x here, I'm going to have 2.4 times 10 to the negative 3. So that gives us the value of the hydronium. And our negative ion. And then for our weak acid, and this is going to happen with all of our weak acid calculations that we're going to deal with, we are going to make that assumption that X is much smaller, less than 5% of a change from our weak acid. So we're going to simply make that assumption that this is going to remain as 0.12 m. And if we do the calculation, we're going to see we get the same thing here. All right, so moving on from there, I'm sorry, check this. We're going to go ahead and plug in our values. So we have our 2.4 times 10 to the negative 3 over our 0.12. Right, so then when we go ahead and plug that in, keeping with the two significant figures, we get 4.8 times 10 to the negative 5. Just remember K is unitless, so we don't include any units with that. So that would be our final answer. All right, we do want to have to show our check to check our assumptions, which I'm going to go through because there's actually two in this case. right, let's start off with the one that you guys are aware of, which is we want to show that that amount of X here is less than 5%. So the textbook likes to use this HPAC, so the concentration of the original weak acid that ionizes, and this is really just X, is equal to the change, X, which is this 2.4 times 10 to the negative 3 over the initial concentration. So 2.4 times 10 to the negative 3 m over 0.12 times 100 is equal to about 2%, which we know is less than 5%. And again, I would be expecting to see this little check where needed. Now we are initially going to kind of work through showing this other assumption that's involved, and that's the whole idea when I mentioned to you that this H3O plus, we know that the water that's present is autoionizing in solution. We need to show that that amount is less than 5% of the hydronium that was from the weak acid. So in this case, we're going to do that the concentration of H3O plus from the autoionization from water is going to be equal to, now we know that the concentration of hydronium in water is equal to 1.0 times 10 to the negative 7. And we're going to put that over the amount of hydronium from our weak acid. So X here. I'll throw in some molar times 100. And you're going to always notice that this is much smaller. So usually, kind of once we get used to these, we'll drop this check. But for right now, it's important just so you're aware and thinking about the fact that that is actually present in water. So we get an incredibly tiny percent, which is obviously less than our 5%. So check and check. All right, I am going to run through one more example of this just to make sure you're okay. If you are good with this, you can try it out on your own and check it. Do whatever you need to do so that you feel confident as you move on eventually to your own practice. So in this one, we're dealing with our ammonium ion, which is going to act as an acid. It tells us that if a 0.2 molar ammonium chloride solution, and again we're focusing on just that NH4 here, has a pH of 5, what is the Ka of ammonium? So just like before, I'm going to start off with the reaction. So we have our ammonium ion. I tend in this case to leave out the chloride ion just because it's going to be a spectator ion. So we're going to have that in solution plus our water that it's going to react with to form our hydronium. Okay, remember this is acting as our weak acid, so it's going to donate a proton to water to form that hydronium, which means that we have ammonia left, which makes sense because it's conjugate base. Okay, our Ka expression is our products over reactants. So we have our concentration of hydronium and our concentration of ammonia over the concentration of our weak acid. All right, so we're going to set up our ice table. All right, and then we're going to go ahead and fill in our initial concentration of our weak acid, which is 0.2 molar. We're going to say again that the amount of hydronium from the autoionization of water is going to be less than 5% of the hydronium from the weak acids. We're going to start with 0. Okay, we know from this it's going to proceed to the right. So based on our balance equation, we're going to have minus 1x for the ammonium and then plus x for our two products. I'm just going to go ahead and simplify that. Okay, and then very similar to what we did before, we're going to use our pH to figure out what our hydronium concentration and thus X is. So I'm going to give a little bit more space there. So hydronium is going to be 10 raised to the negative pH, so 10 raised to the negative 5.0. All right, and then keeping with our 1 sig fig, which is at 0.0, remember we're going to have 1 times 10 to the negative 5. All right, we can go ahead and plug that into our ice table. And then same thing in this case, that is going to be much less than 5% here. So we go and simplify this we're going to still end up at 0.2. All right, now that we have all of our values, there's nothing else we're looking for in the Ka expression, so we can go ahead and solve for that. So our Ka is going to be 1 times 10 to the negative 5 over, oops, sorry about that, over our initial. Okay, and then keeping with the 1 sig fig that we have going on here, we end up at 5 times 10 to the negative 10. And that would be our final answer there. Okay, and then just like before, I just want to walk through again those 2 assumptions. So we're going to check. Okay, we want to show that the concentration, NH4, that ionizes, which remember is just X, is going to be less than 5%. So this is going to be our 1 times 10 to the negative 5. That's our change. That was our X over the initial 0.2 times 100. And that gives us definitely something very much smaller than 5%, which I didn't even write down. So that checks. And then finally, we have the H3O concentration from the autoionization of water. Okay, remember the concentration from the autoionization of water is going to be 1 times 10 to the negative 7 over the actual concentration of hydronium from the weak acid that we found based on the pH times 100, and that's also, when you plug it in, less than 5%. Okay, so those are just 2 examples of how to find Ka for a weak acid. You can go ahead and move on to the next video.